Good morning. Today we will start lecture number 3 of the module Robot Dynamics and Control. Let us see what we studied in the last class. We have seen in the last class the dynamics of robot manipulator, a general case for N-link manipulator. What we saw was basically a procedure how do we get dynamics of the N-link manipulator. Okay, we saw we have to first do kinematic analysis, and then based on the kinetic energy and potential energy of the manipulator, we use Lagrange formulation to get the dynamics of the manipulator. And then we had a look at introduction to control. Okay, some basic fundamentals of the control we revived. Okay, in terms of control implementation, what are the different types of controllers available and things like that. Okay, in the today's class we are going to study actuator dynamics. Okay, how to integrate that actuator dynamics with the dynamics of the control, dynamics of the robot manipulator. So that integration part we'll see, and then we'll use our understanding about control to develop some simple control algorithms for basically point-to-point movement of the robot. Okay, that is what we are going to do in the today's class. Okay, let us first start with the actuators. Now, what are the different kinds of actuators that you know for robot? There are motors, electrical domain actuators. Then in the hydraulic domain you have hydraulic actuators. Okay, these are the most popular actuators for the robot. Okay, so now in most of the robots, like the motors or actuators that are used are servo actuators. Okay, they can be hydraulic servo or they can be electrical servo motors. Okay, now in terms of motors, there are different types of motors possible. One is DC brush and brushless type of motors. So DC motors is one class, and AC motors is another class. Now here is an example of one of the motors in our robotics lab at IIT Bombay. Then there are AC servo motors possible. So depending upon the application, like different motors can be used. Okay, then you have a hydraulic actuators, and then for hydraulic actuators, you know the equations of dynamics, they are nonlinear. So we will not get into the dynamics of hydraulic actuators. We will first see today the dynamics of the motors, which are most popular in many robotic applications. The hydraulic actuators are used in the cases where you need a very high power robot. Okay, and or else you need a very high performance, high speed in the case of robots. So that is a place where you use hydraulic actuators. So we will not get into the dynamics of hydraulic actuators in the interest of time today, but we will see in detail the dynamics of the motor. Okay, so let us come to the motor dynamics. There are mainly two parts for the motor dynamics. One is mechanical part of it and electrical part of it. Okay, now you see this is a free body diagram of the armature of the motor. Okay, you see there are terms which are damping in the motor. Then this is a electrical torque generated in the motor. Then this is motor motion theta m. This term tau k over n is a term which is a contribution from the robot dynamics. Okay, where n is a gear reduction ratio. Now if you do the balance, torque balance on this armature, you get these are the mechanical domain equations governing the motor dynamics. So the contribution from the robot manipulator comes over here. Okay, and this is a motor torque generated, which is proportional to the current which is going in the motor. Now let us come to the electrical part of the motor dynamics. So you have this resistance of armature, inductance of armature, and then this is a motor which generates this back EMF corresponding to the speed. So here if we do now the circuit voltage balance, you will get these as a equations of electrical part of the motor. So your voltage given or supplied to the armature is balanced by IARA, resistive heat loss, then back EMF and inductance of the motor. Okay, this back EMF is proportional to flux and speed. Okay, this omega is nothing but theta m dot, which is a motor speed, and then this back EMF will be given as k times flux into theta. Now usually this inductance term is very small, hence we can neglect that term. So with that our equations will get reduced to this form. Now from here we can find out this current value I to be equal to VA minus this back EMF. Now usually this flux is a constant flux. Okay, this flux is basically a property of the field of the motor. So in field, like you have a constant voltage, or in a permanent magnet motor the field flux is constant. Okay, so because of that you can absorb this constant into this constant to have new constant KB, which is corresponding to the back EMF, and then multiply it with theta m dot. Okay, so this is how your current will look like. Now this current you can substitute in here, and then this whatever torque you get you substitute in this equation, and then you will get these following equations of the motor dynamics. So you have now both mechanical part and the electrical part of the dynamics coupled together in this equation. Okay, this RK is a new term introduced corresponding to the gear reduction ratio, and then this RK is given by 1 over NK. So now we can rearrange these equations and introduce this subscript for the kth joint for robot manipulator to get these equations of motion. Okay, you observe that these terms are kind of effective damping terms. Okay, and then this is your input, which is something which you can control or you can command. Okay, so this is where your actual robot command is going into. So now how we can combine these equations into robot dynamic equations. Okay, so look at the robot dynamic equations what we had seen. They look like of this form: dq double dot plus cq dot plus gq is equal to tau. Okay, now this is a vector equation. Okay, this is a vector matrix equation. These are the matrices d, c, and this g, tau, they are vectors, and these two are vectors, q double dot and q dot. Now this is a corresponding form for one of the joints or one of the links of the robot. Okay, you remember this form we derived by using Lagrange formulation, basically kinetic energy, potential energy of the robot. So this is a standard form of the robot dynamic equations. Okay, now we have to combine this with this motor dynamics. These are the equations of motor dynamics as we have just derived. Okay, so this is actuator dynamics. Now this can be like the equation of other actuator also, like whatever actuator is there in your particular robot that you are considering. So this can be like hydraulic actuator equation also. Okay, but the way in which like the robot dynamics and the actuator dynamics they are combined, that remains the same. Okay, so you just understand the way in which these two are combined together. Okay, so now what we have to do is we have to substitute this tau k from robot dynamics into the actuator dynamics and see what we get. So by this substitution we will get this equation, where now these terms are remaining the same up to this point. This input is also remaining the same, only in place of tau k, which was kind of a load torque on the motor. Now the motor load is basically because of this, all these terms in the robot dynamics. Okay. So physically you can interpret that this is a load coming because of the dynamics of the actuator, dynamics of the robot link. Okay. Now we can make use of this relation. Your generalized coordinate of the robot is given by gear reduction multiplied by actuator rotation. Okay. So if you make use of these and convert everything into theta mk equations, we get something like this. Now here you observe that what we have done here is we have taken the term corresponding to k equal to j out of this equation, this part of the equation, robot dynamics equation, and then used this formula and brought over this term over here. Okay. So you see this rk square into dkk of q is an additional term to the inertia of the motor. You see this? We will come to this fact why we have done this thing, but this is a mathematical manipulation we have done to get some simplification. Now what remains here is the summation, but for j is not equal to k. Okay. Now let us see, we will call this inertia as a effective inertia. We call this matrix term, this B matrix or B damping term, to be equal to B effective. Okay. Remember, we are doing this for a single link of the robot. So this can be done for each of the links. Okay. You have to do it for all the links like this, and then you can develop the control. So next thing we do is we have this dk term substituted for all these nonlinear terms. Okay, this dk is nothing but a disturbance. We can imagine this as a disturbance on this system. Now you see, observe that this system is getting reduced to a linear system with disturbance. Okay, we will question that this term here has still a nonlinearity in terms of this q. Okay, so as your robot is evolving, okay, this term, inertia term, is changing. Okay, but we can assume it to be some constant inertia term. Okay, for some averaged value of the inertia, okay, over whatever range your robot is operating, okay. So finally we will get this equation governing the actuator and robot dynamics both combined together. So see, this k term is kt over Ra, and this type of equation we will get for each of the robot link. Now we will just focus on one link and develop the control for that, and entire procedure remains the same for all the other links, okay. So we will do it for only one joint henceforth, okay. So now let us see first a couple of control strategies which are very simple, which are very intuitive, heuristic kind of a control strategies, okay. So actually we have two types of problems in all the robot manipulators. First is a regulation problem and second is a tracking problem. We have seen this before. What is a regulation problem? You have to move from one point to another point. You don't care how do you move, like, or what is the trajectory traced by the end effector moving from one point to another point, but you have to just go from one point to another point, okay. That is a regulation problem, or it is called a point to point control problem, okay. Another type of a problem is a tracking problem, okay, where you have to track this trajectory. You have to go from starting point to the end point in a specified manner, okay. In this particular case we are seeing the straight line trajectory, but it can be in general any trajectory. It can be a circle, it can be parabola, it can be any trajectory, okay. And now what we are considering is that we are interested in slow point to point motion, okay. So we want to move to this final point in a very slow manner, okay. And then you term theta d as a final desired joint vector. Now you know, by using inverse kinematics you can find always the final joint positions corresponding to final end effector position, okay, by using inverse kinematics, okay. So you have to do that before you proceed for development of control, okay. So this theta d is basically a final desired joint vector, okay. Now let us see how we design control. So recall that our robot and actuator dynamics equation combined together looks something of this form, okay. Now this is the most simple kind of a strategy one can think about. You have this desired position, you subtract from the actual position, and then that is what you get as an error. You multiply this error with some proportional constant, okay. That plus similar thing you have done here for velocity. The final desired velocity is 0. You have subtracted the actual velocity of the motor, s theta s, the actual velocity of the manipulator or motor joint, and then you have used it as another term in your control expression. So this is called a proportional and derivative feedback. So in simple terms it's called a PD compensator, okay. So with this now we will see how we can analyze our original system. So we have to take the Laplace transform of the original system and then substitute for this control law in the expression. Then we will get this kind of a expression for motor dynamics So motor dynamics evolves according to this expression. Now recall that your D term has lot of nonlinearity. Okay, it contains lot of nonlinear terms. So this part is acting as a disturbance part, and this part of the equation is governing theta m, kind of a transfer function between theta m actual motor position and the desired motor position. Okay, do you see that? So actual motor position will not be equal to desired motor position because of this term, because of the disturbance it may not be equal to, but when given that disturbance is equal to 0, you will have actual terms matching with the actual position of the motor matching with the desired position. Okay. Now this omega s is a characteristics equation. So this is given by this characteristic polynomial. This characteristic polynomial is dependent on J effective, B effective plus these gain factors coming because of your control law. Okay. Now this whole thing can be seen, we can represent this in terms of a block diagram in the following fashion. Okay. So this is a block diagram. You can see here, this is your plant or this is your robot manipulator. Okay, it has this disturbance term coming in here, and then this part is like a linear part of the equation. This is the equation. This linear part is represented over here by this block and the next integrator block. Okay, so here the output is theta dot m, and then you integrate it to get theta m. Now you can see that your kd gain and kp gain, they are constructing your control law Vk, PD control law in this fashion. Like you take theta dot m, multiply it with kd, okay, add that into the error theta m minus theta d m, desired position, that error multiplied with kp, you add to the derivative part. Okay, so this is output here is a PD control part. Okay, then that multiplied by this k will give you term over here. That term you from that term you subtract this disturbance term, and then you generate this part. Okay, that is how this block diagram is generated. You see that? Okay, now let us do some kind of a analysis with whatever we have developed so far. Okay, now if you use some theory about linear systems, the transfer function, basic fundamentals of automatic control, then you will find that this closed loop system, which is formed because of the combined motor and robot dynamics with PD control, okay, that is your system now. Okay, you see, important thing to note here is that for different types of controllers you will have these different closed loop systems. Okay, you got to do a separate analysis for each one of them. For all the controllers, it is not like you will get the same equation. For different controllers you will get different equations and then different systems, and you have to basically do analysis for each of these systems separately. Okay, so you see, for this particular case, when we are having PD control, now if we see the error in the regulation, it is given by this expression. So now you substitute for theta d from the previous expressions, or you can use the previous block diagram, okay, to see how the error at this point will look like, okay, and then you will get this expression, okay. Do you see that? This has this characteristic polynomial omega, and the term corresponding to this part will show up over here now, okay. So this is your error expression in the S domain, okay. So now let us say if we are interested in what is a steady state error, what happens in the steady state, like we allow enough time for the manipulator to go from initial position to final position, and what is now the final position steady state, whether there is an error in the steady state at the final position. That is what we are interested in looking at. So let us see the steady state analysis with this. So commanding manipulator to go from initial position to the final position means that you are giving some kind of a step input in theta d, okay. The desired position you have from whatever initial position, we have to go to the fixed final position. So it's kind of a step we have to take to go from initial position to the final position, okay. So now let us have a look at what is a steady state error. Now before that, we have made here one assumption that the disturbance is constant, okay. We'll worry about like what happens when disturbance is not constant little later, but just assume for the sake of analysis that we have some constant disturbance term coming into picture, okay. With this constant disturbance, what is my steady state error? So if you do the analysis again by using the Laplace domain tools, we know that from Laplace analysis that steady state error will be given by limit s tends to 0 of s into Es. Es is an expression for error which we have derived previously, and if we now plug in, see this is a previous expression for Es, okay. Now let us plug in that here, and the steady state error we'll get is of this form, okay. So the steady state error in the response curve is represented by this. So when time, or when you allow sufficient time for things to settle down, and see now what is the error between your initial, your desired position and the actual position, you'll see that is a steady state error. So this is theta d commanded step response, and then this is evolution of the theta m with the PD control, and then this is finally steady state error. So we see that there is a finite steady state error when you use PD control. Now this error is smaller for higher gear reduction, okay. Higher the gear reduction, the smaller is the error, okay. And another thing you observe here is that it can be made small by increasing the gains, okay. So you go on increasing the gains of PD control, and then you'll go on reducing the error, okay. So these are the two ways. Like suppose if we want very small error, then we have to use very large gains if you are using just a PD control strategy. When we use a larger gains, then it may lead to system instability, or it may have undesirable transient response of the system, okay. Sudden movements or oscillations of the system. When we increase the gain, we are basically increasing the natural frequency of the closed loop system, okay. this may lead to increased oscillations in the system. Okay, so when we are thinking about robotic applications, we never are interested in having these oscillations in the system. Okay, we don't want links to go and oscillate about the final position and come to the rest in the final position. We want it to go and steadily stay in the final position. Okay, so that is very important from the control point of view. So you cannot have like very high gains. So how to now eliminate this problem? That is a question that we'll see later. Okay, let us see how we'll select the gains first now. Okay, so you recall now again the transfer function between theta m and theta d, okay, is given by this expression. Here we have assumed that disturbance is 0. Okay, now this is a characteristics polynomial, and from this characteristics polynomial you observe that this is a second order kind of a behavior. Okay, of course here you again recall the assumption that our J effective inertia has some terms which are nonlinear, but we are assuming them to be some constant terms, okay, averaged over the range of the operation of the manipulator. Okay, so if we compare this behavior with our standard second order behavior, you recall the standard second order behavior, s square plus 2 zeta omega ns plus omega n square. Okay, that is a standard spring mass system equation, second order standard behavior. Okay, now if we compare these two, we will get the expressions for omega and zeta in terms of your gain parameters, gain and J effective, B effective, these parameters. Okay, so we will get these expressions for omega and zeta, which are closed loop natural frequency and damping. Okay, these expressions are given here like this, and then from these expressions you can find out values for Kp, gain Kp and gain Kd. Okay, now what you need to do is to select your zeta and omega. See, zeta is, as I said earlier, you have to have a non-oscillatory response. Okay, so best way is to choose zeta to be equal to 1. Okay, so that is a critical damping. You can choose for over damping also, but then like that's not much desirable, because the response becomes slow then. Okay, sluggish response will be there. So it's not desirable to do that. So basically you choose zeta corresponding to critical damping. Okay, so that way your zeta gets fixed, and then from this expression you can find Kd given omega. Now omega selection you can do based on how fast you want to move. Okay, now again recall the trade-off that I have told you already, that you can ask the robot to move from one point to another point as fast as you want, but you have a limitation on the actuator. Okay, so there is always balance between how much energy you have, okay, and then how fast or how much performance you are desiring out of your robotic system. Okay, so this trade-off you have to balance and accordingly choose this frequency omega, and then your gain values will be in place. Okay, so always after choosing your gain values you have to see over the response, like in the simulation, like over the range of response of your system going from initial position to the final position, you see whether your input is anytime exceeding the saturation limit. Okay, there will be always a limit put by the motor. So see whether the system is exceeding those limits. Okay. Now let us see one simulation example, not for the actual robot, but kind of using the similar equations. We have carried out this simulation. So in the Simulink in MATLAB, you can construct a model of this kind, where you have, this is an integrator block, where J effective and B effective in this transfer function are assumed to be 1. Okay, and then this is your K gain, this is your Kp gain, and this is your Kd gain. Okay, so this is a PD control example simulation, and then we want to study now, if we vary this Kd gain, how the response is going to look like. So the next slide shows the response of the system for variation in the derivative gain. Okay, for various derivative gains you have this response. So you can see, as you increase the derivative gain, the oscillations first die out, then your response goes on becoming sluggish, goes on becoming slow and slow. Okay, so the system takes like more time now to reach the final position when the derivative gain is high. Okay, so your settling time will be increased with the derivative gain. Okay, so you have to write a derivative gain, not to have system go in the oscillatory fashion, and also not to have system going too slow or too sluggish. So these are the two criteria you have to use to choose the derivative gain. Okay, so next let us summarize what we have seen for the PD compensator. First, we saw this strategy is very simple to implement. Okay, then PD control is good for slow point to point control. Okay, see, if you want to go for very fast from one position to another position, this is not a good control strategy. Okay, we'll come to that as we go along. You'll understand why I'm saying this is not a good strategy for that purpose. Next, the large gain values are required in PD control. Why large gain values are required? Basically to have lower error, steady state error. Okay, then steady state error in PD control cannot be eliminated altogether. Inherently PD control will have some error. If you have disturbance corresponding to that, there will be some error. Depending upon the gain values, you can control that error values, but there will be some error. It's not that ideally there is a zero error in PD control in the steady state when you have a disturbance of the PD control. Next is PD control often leads to saturation of the input voltage. Okay, especially when you are going for a very large movement of the robot manipulator, like your starting point and final point, they are located far apart. Okay, then initial error, you can imagine that initial error will be very large, that is multiplied by a Kp value, so that gives you very large term which will typically exceed the saturation limits of the motor. Okay, so this PD control will often lead to saturation. So now how we overcome some of these deficiencies? The answer is PID control. Okay, so let us look at the next strategy, which is PID control. Now recall again the combined equation of the robot and the actuator dynamics in this fashion. Now to overcome this deficiency of the PD control, the most important, the steady state error part, you introduce this integral control action. So what this action does is basically it takes the error value, it is integrating it over the time. So in the steady state, you imagine that you have this constant steady state error value, and now you are integrating that and you are generating. So integration is nothing but this area. So as time proceeds, this integration is going to increase, this area is going to increase. Because of that, like you are now implementing that thing on the robot control. So because of that error is will slowly start decreasing. So for higher and higher time, like you are doing this integration, and like larger and larger value you are trying to apply on the robot manipulator. So that will eliminate the steady state error. So this is how the steady state error is reduced in the integral control action. Okay. So that is why we introduce integral control action. That is a basic motivation. Now with this controller's transfer function is given by this expression. So this is a controller transfer function. This is a controller transfer function. Now let us see how it looks in a closed loop fashion. So closed loop system will be now of a third order. So this is omega 2, which is the next this different characteristics polynomial. Okay, in PD control this was omega, which was second order characteristic polynomial. Now this is a third order characteristic polynomial. And as I explained earlier, the steady state error in the PID control will be eliminated. Okay. So this is a basic advantage of using PID control. And now you can tune again the gains of PID controller to suit your application requirements. Okay. So this is how the PID controller will look like in a block diagram fashion. So you have entire thing same as the previous block diagram for PD control. Okay, this entire thing is same, and now you have added one more term in your control expression corresponding to integral control action. Okay, this is how your PID controller will look like, and then this disturbance is still entering your robot equations. Fine, now let us see some analysis. So PID control, you can apply root stability criterion, which you have studied in the automatic control course, and with this stability criterion, when we have a zero disturbance, there is no disturbance acting on a system, we get this expression for stability of the system. Okay, the system will be stable if this integral gain is less than a particular value, which is in general dependent upon the derivative gain, proportional gain, and motor or your manipulator parameters. Okay. So now this implies that if Ki is increased beyond certain value, your system is going to go unstable. Okay. So that means like your integral control action in some sense is introducing some kind of a instability in your system. Okay. So you have to be very careful when you use integral control action, because it is always leading to some kind of a instability, into introducing some kind of a instability into system. Though it takes care of steady state error, it has this behavior. Okay, so one has to be careful about introducing integral control action, and that too very large integral gains. Small integral gains always will take care of your steady state error, but when you want to use large integral gains, you have be little careful about that. Okay, because it is introducing some kind of instability into your system. Okay. Next we will see the simulation similar to what we did for PD control. Now here is this simulation model. All the other parts are remaining the same in the Simulink. Okay. Only this new block diagram is added to Simulink model corresponding to integral action of the controller. Okay. Now with this we would like to study what will happen if I go on increasing the integral control gain. Okay. So that is a simulation carried out, and the next slide shows you the simulation results. So you can observe clearly here that the steady state error is taken care of. You are reaching the final position. Okay, but when you increase the gain values from these, the kind of order of magnitude change, then you see that your response becomes oscillatory in nature, and again the settling time goes on increasing. The time it requires to take the final position or fixed final position goes on increasing. So this is not desirable. Okay, so we have to limit our integral action to a certain value so that there is no oscillatory response of the system. Okay, so system does not go into oscillatory mode, that we have to ensure. And most of the robotic systems, that is true. Like, I mean, you should not have any kind of a oscillatory response in the robotic system. Okay. Now let us summarize our PID control compensator. So again, this is a strategy which is simple to implement. Okay, very simple to implement. You don't have to have any nonlinear computations done. We'll see next why in some other strategies we have to do these nonlinear computations. But in PID control, we don't have to do any nonlinear computations. It is very good for slow point-to-point motions of the robot, mainly because now it is taking care of the steady state error. Okay. Now again, this steady state error is eliminated. Then lower gains, we can use now lower gains. Because of the integral control action, we don't have to use very large gains to have smaller steady state error. Okay, as in PD control. So here we can use lower gains, so you can avoid saturation of the actuators. Okay, this is very important in terms of control implementation. Now the problem with this is the fast motion with very high performance is not possible. Okay, because these nonlinearities which are there, or disturbance D term, we are not doing anything about that term. We are just taking care of that term by using these PID control gains. So because of that term, you will see that there is always going to be slow response, like the response will not be very fast, or very high performance you cannot expect from PID control kind of a system. Okay, you can tune the gains to the maximum extent possible, but then still, like, because of this disturbance that is not taken care of, there will be some kind of a leeway available for performance improvement if we take care of this D term. Okay. Now let us summarize what we have done today. So PD and PID controllers, basically we found out first robot and actuator dynamic equations, and then we have reduced them. See, you can observe now what we have done is that we have reduced these equations to a form which is very similar to a linear form with nonlinear disturbance term. This is sheerly from the point of view of development of control. Okay, we wanted to develop good control based on some linear techniques that we know already. So because of that, we have done this manipulation. Okay, we see now the system robotic system as a linear system with some nonlinear disturbance. Okay, so these kind of manipulations or this kind of variations you have to carry out. You have to have different perspectives of looking at your robotic system, so as to develop different kinds of controllers. Okay, so next, like in the classes to come, we'll study like how we can develop a purely nonlinear controller based on the same equations. Okay, without like neglecting couple of terms, or without like considering the terms to be nonlinear or acting as a disturbance. Okay, so we'll see that in the later classes. So this was our equation that we got by considering this linear form with the disturbance term here. Now then we saw different PD and PID control algorithms for this point to point motion, regulation motion. Then this strategy is ideal for robots where there is a very high gear reduction at the joints, because of the higher gear reduction, the nonlinear term, disturbance term that we have neglected or that we have considered as a disturbance will be smaller. Okay, so basically because of that very high gear reduction, this is an ideal strategy. But if we have a robot where the motor is directly connected to the link, okay, there is no gear reduction, then I think this strategy should not be used, or this will not give very good performance. Okay, even for point to point motion. Okay, so you have to be careful when you are using this strategy. You have to see whether the disturbance term, how much is its contribution. Okay, then when we have to carry out tasks which are slow, like you have to move slow, like you have to transfer material from one place to another place, pick and place objects from one place to another place in a slow fashion, then basically you can use this kind of a strategies. And then there is one more kind of a mode of robot operation where you take the robot physically through different points, okay, end effector through different points, okay, yourself, and then record those points with in the memory of robot, and then you can command now to go from whatever points you have taught the robot. Okay, so this is a teach and play back kind of a mode of robot operation, where now there is no like you don't have to worry too much about robot dynamics. All the nonlinear dynamics you not to worry about too much, or inverse kinematics analysis you don't have to do in this case, because like you are physically taking the robot through different points that you want it to be carrying out the motion. Okay, so that is a important advantage of this teach and playback mode. So you'll find in the industries, like many industrial robots, they are operated in this fashion. There will be teach pendants with the robot, and then you can record, you can take the robot through different desired positions and then record those values of the joint angles in the memory of the robot. Okay, now this strategy, like whatever strategy PD and PID strategy we have seen, can be extended to slow motion through several points. Okay, you can specify several points next to each other, and then like you slowly move the robot through these points. Okay, so this is in very crude fashion, like you are tracking some trajectory, but very crude fashion. Here the tracking trajectory points, they are not very closely placed, they are kind of far apart. Okay, and then you use PID control strategies to take it through these points. Now there is no need for computation of complicated nonlinear dynamics, okay, in this case, and then you can use other strategies in the linear domain based on state space tools. We will not go through these strategies, but I should mention this point that you can use, there are so many other strategies that are available in the linear domain. We can we can plug in those strategies and we can apply here for the this particular linear kind of a form of a robot manipulator equations with disturbance. And then main drawback is you cannot use this for the trajectory tracking kind of applications. So these control strategies, they are mainly for point to point kind of a control. Okay, so here we'll stop now. In the next class we'll study now trajectory tracking algorithms. We'll have look at these algorithms like method of computed torque, feed forward controllers, and then also we'll have some fundamentals of nonlinear controller studied in the next class, so that like we will prepare ourselves to understand now a nonlinear domain of control tools. Okay, so there are many nonlinear strategies that are very efficiently available. I mean, there are very efficient strategies available for robot control in the literature. So we'll have a look at a couple of them, and then that will like close our chapter on robot control. Okay, so we'll stop here.